Hey everyone, thanks for coming out. Thanks for coming out to another public AstroNight here from Astro McGill. So just as a show of hands, how many of you here, is this your first AstroNight? Okay, cool. Anyway, thanks again for coming out. So first, many of you entered a raffle on the way in. So we'll have draw a ticket to see who won one of our beautiful Astro McGill t-shirts. Okay, so the last three digits are 946. All right. All right. Yeah. In this household for not seeing the sun for 6 months. All right. Okay, so we're happy to welcome back Etienne Bourbeau. He did his master's here at McGill, and you may recognize him from a past public talk from then. But now he's moved on from working on the highest energy light we see in the universe to even higher energy things he's going to talk about from the South Pole, neutrinos from all around the universe, and he's going to talk about these tonight.
So, thank you, Dr. Archibald, for the intro. That makes more sense. Okay. Okay, cool. Can anybody hear me at the back? Is that good? Awesome. So, I'm here today to talk about cosmic neutrinos, more specifically about how these neutrinos, which we'll see are really weird particles, can be used in astronomy to decipher basically what amounts to a really puzzling universe. So I'm going to start by explaining what do I mean by messenger. I'm going to cover a bit the messenger that astronomers have used for a couple of years now, if not centuries or millennia, to gather information from stars, galaxies, planets, and so on. And then I'll go on describing why we need a new messenger, a new particle or thing that's going to come from space and give us answers to the questions that we have. And so I wasn't sure how to begin this presentation, and then I figured I'm an astrophysicist, and well, if you study astrophysics or astronomy, usually everything starts with the universe. So let's begin with the universe. So the universe is big. It's really big, so much so that it's really a problem because things are so far apart. That stuff I'm mentioning here is so far from us that we cannot visit it. It would take us way too much time for us to visit planets and other galaxies. And so we have to rely on informations that these objects, these galaxies, transmit through the vacuum of space, and be lucky that that information arrives safely at Earth so that we can basically understand it. And so far, over the last millennia, ever since people started looking at the sky and the stars, we've mostly relied on a single messenger, and that messenger is light. Whether we look at it through the lenses of a telescope like Galileo did back 400 years ago, or whether we look at it with more powerful instruments, with ground-based telescopes or space-based observatories like the Hubble telescope, all our knowledge of what's out there, what's around us, planets, stars, galaxies, and even the universe, how it is evolving, how it evolved in the past, all that information has been gathered through looking at light and decoding, basically, light. And so light comes to us in a variety of different types. So light can carry a different amount of energy depending on the type of light that you're looking at. And so this energy, the quantity of energy that light contains, is described by what we call the electromagnetic spectrum, which you can see here. And so depending on the energy that light carries with it, you're going to be able, if you're an astronomer and you look at that very particular range of energy, you're going to be able to obtain different informations about the world we live in. So for instance, if you look at radio wave, which are the lowest energies that you can find, if you take radio telescopes, you look at the sky, you're going to see something like this, which actually showed up at the quiz right before the talk. And so this is the very first light that was able to be emitted, that was emitted by the universe at its formation. It's what we call the cosmic microwave background. And this background radiation has been used by cosmologists to gather a lot of information about what was the state of the universe when it evolved from the Big Bang. So you can gather an incredible amount of information about the expansion of the universe, the density of matter when it was really, really compressed and really, really hot. And so this is what you can observe, for instance, in radio waves. Now, if you move and look at a range of energy that's a bit higher, you look at light that we can see with our eyes, like optical light, or light that contains about the same amount of energy, plus or minus, that we call the infrared or the ultraviolets. And again, you look at the sky looking for this particular range of energies, the portrait of the universe is going to change drastically. So what you're going to see first is basically our galaxy and the stars around us, because what we've learned from this is that most of the infrared light and UV light that you can see comes from stars. And from this, we learn a lot about how stars form, how they evolve, and what happens to stars when they reach their end of life. Now, if I look at this and I switch again my range of energy that I want to look at, I look at higher energy light that's called X-rays. Again, we leave the picture that we know, which is our galaxy, and we start looking at weird features that appear in the sky. In this case, when you look at X-rays, you're looking at very, very dense and hot gas that are circling and being produced and heated around the center of the galaxy, on which lies a supermassive black hole. And so when you start looking at very high energy light, you start investigating high energy processes, like how supermassive black holes work, how this gas, how these stars at the center of the galaxies that are so close to each other move around and stir up matter to the point where it heats up at thousands of degrees and emits this X-ray radiation. Finally, if you go really, really far and look for the highest energy light that you can find, what you're going to find is what we call gamma rays. And then gamma rays have this particularity that because they are so energetic, the particles of light or photons that are produced in gamma ray energies, they're so energetic that they're going to cross great distances. So much so that besides seeing gamma ray sources around our galactic plane, which is basically the line that you see at the middle, you're also going to start seeing spots above and below that line. And these spots actually corresponds to galaxies. More specifically, the highest, the more violent galaxies that have, again, black holes and other very violent phenomenon that produce explosions, among other things. And so with gamma ray, our scope of view extends to a lot of very, what we call extragalactic sources. So we're looking really far away compared to the visible, for instance. And so this is all great. So like we see, depending on the light that we choose, we can gather a lot of information. And we've become pretty good at understanding matter. And by matter, I mean the stuff that makes stars, that makes planet, that makes you and I. Basically, we've gathered an incredible amount of information using light as our cosmic messenger. However, when we make calculations and we look at the universe and we want to know, well, how much energy is there in total in our universe? And then we look at the phenomenon that we know with matter and so on, we realize that all that stuff from the previous slides, it actually accounts for 5% of the total amount of energy that's contained in the universe. So there's this entire 95% of the pie chart of matter or energy that we call dark matter and dark energy, which has this very annoying particularity that it doesn't produce light or it doesn't interact with light. So you can't use light as a messenger because it does not carry information about 95% of the universe. So that's a problem if you want to figure out what the heck is the universe, what's going on there. And so because we want to know what dark energy is, what dark matter is, we're trying to look to other ways to gather those answers to our questions. And additionally to that, there's also weird objects like neutron stars or supernovas, which we still, even though it's made up of, we think, normal matter, it's still difficult to understand the physical processes behind these explosions and very violent phenomenon. So it would be useful to have another way of looking at these processes. Now, another reason why we would be looking for another messenger is that light as a transmitter of information is not a perfect messenger. So for instance, in a perfect case, if I want to look, if we're on Earth and we want to look at a star that's nearby, say 1,000 light years, usually photons or light particles are going to do their job. So, which means the sun is going to emit light. That light is going to travel through space in a straight line, which is useful because when you receive it, you know where it came from, and so you know, oh, there's something there going on. And then it's going to tell its story about a sun in that, or a star, or so on. Now, if you want to look at the same type of star, but across our galaxy, if you want to look at a star that lies on the other side of the galaxy, so between you and the star, there's going to be millions of stars and other objects, namely dust in between the stars that we call interstellar dust. That's going to be in the way of the light that's coming towards you. And so what usually happens is that the light is going to interact with that dust. For instance, if you look at visible wavelength, it's going to interact with that dust, scatter or get absorbed and re-emitted in another form of energy. And even though you're going to be able to see, well, that looks like a sun pretty much, you clearly don't have a perfect image at the end because some of the information has been entangled with noise, and it can become really difficult to interpret what's going on when you have so much interactions between you and the source or the star that you want to look at. So this is an example where you see the clouds here. This is not dark matter. It's just that the light from the stars that you see in the clear spots are absorbed basically by these clouds of dust. And so they make these dark regions that prevents us from actually looking at the objects that lie on the other side. Now, that's for light. I'm talking mostly about infrared light and optical wavelengths. But like I said earlier, gamma rays, like the highest energy light, can travel really, really far and doesn't really care about the stuff you put in the middle. So it's going to see a dust cloud, it's not going to care, it's just going to go straight. And you're going to see gamma ray from most of the sources. But the problem arises when you want to look at something that emits gamma rays, for instance, this weird, very violent phenomenon. And you want to look at a phenomenon that's really, really far away. So we're not talking about 1,000 light years, we're talking about 1 billion. So this is approximately the distance at which, the further you look in the universe, the more you go back in time. And so at this distance, you're trying to look at the very first events that formed galaxies, the very first explosions in that case, because you look at high energy gamma rays. And unfortunately, there's that light that is emitted from this explosion has to travel a really long way. It's going to take it theoretically 1 billion years to reach the Earth. And it's such a long way that there's 100% probability, actually, that in its path, the gamma ray photon is going to bump into another photon, which could come, for instance, from the microwave background, because there's a lot of light that's just lost and travels randomly in space. And so upon meeting that other light particle, the gamma ray is going to interact and produce charged particles, namely an electron and an anti-electron, which has the same mass as the electron, but has a positive charge. And so now your light particle, your photon, has transformed into 2 charged particles. And so they would carry on continuing in a straight line towards you, were it not for the fact that charged particles get influenced by a magnetic field. And because the Earth has a magnetic field, because stars around us have magnetic fields, because galaxies have magnetic fields, these particles are going to end up curving around and moving and twisting. And so much so that, sadly, you're not going to be able to see that object that sits really far away, leaving us really hungry for more answers. So this is a more formal representation of what I was talking about. On the horizontal axis, at the top, you can see the range of energies that light has, like I showed earlier. And on the vertical axis, what you see is basically the distance scale. So at the bottom, those are objects that are really close to us, like the galactic center. I mean, close in terms of, still a couple of thousand light years away. But and then at the very top, you see there's these cosmological maximum, which is basically as far as you can look and still see that stars are forming, because prior to that there were no stars. And you see that there's this big white region there that says it's opaque to photons. So if you want to look, for instance, at very high energy phenomenon very far away, you're not going to be able to use light. And so our goal here is to find another messenger. So the name of the talk pretty much spoils the answer. It's going to be a neutrino, but we're looking for another messenger that could help us fill out that blank. And so when we start to look at other messengers, we see, well, there's so much we know about matter. There are only so many fundamental particles that move around. So we're all made of atoms. These atoms are made of protons and neutrons and so on. And so you can break down matter into a very relatively small list of particles. And that is what particle physicists call the Standard Model, which lays down all the particles that make up the known matter or known universe. So usually the Standard Model is quite complicated because it's particle physics. And you're going to see right now, you're seeing weird names like quarks, bosons, gauge, leptons. Those names are probably not familiar. You're not familiar with them. So let's just simplify things by sorting these particles into 3 categories. So first, in purple, you're going to have those quarks, which are actually the building blocks for protons and neutrons. So basically anything that ends up in the nuclei of the atom. And so at the bottom, you can see what amounts to the electron and its extended family. So little did we know 60 years ago that the electron actually had fat cousins, 2 of them that we know of right now. So these are particles that have the same electrical charge as the electron, but are more massive. For instance, the muon in the middle is something like, I think, 400 times the mass of the electron. I'm maybe wrong like that. I should look up the Wikipedia once. And so the neutrinos, like we'll see later on, they're also part of that family. And so those are the electron and its family. And then on the right side of the figure, what you see are bosons, which are basically carriers of the fundamental forces in physics. So there are three forces here that are carried by particles. The electromagnetic force, which is what photons are all about. They carry that fundamental force through space. And then there are some other bosons that take care of what we call the weak and strong nuclear forces. But again, because they're not really relevant to our purpose of looking for messengers, we're just going to call them Jedis because they carry force. They carry the force with them. So now, what can we use as a messenger? Well, we've used the photon. We've already covered that one in depth. Now, all these particles that are underlying in that square, they all end up producing charged particles. And so because they produce charged particles, you end up in the same situation as the situation with my electron and anti-electron with the gamma ray. So they're going to be diverted by a magnetic field, which means that if you want to do astronomy, it's going to be hard because you detect a particle, but you don't know where it came from. So you can't really do anything with it. And finally, the other Jedis, the force carriers, well, these are particles that only appear and disappear upon interactions taking places. So they are really short-lived particles, and so they're not well suited for traveling, for instance, billions of years in space, because they're just going to appear and disappear whenever there's an interaction going on. So that's out of the picture. And so what we're left with are these three particles, which are called neutrinos. And I'm going to talk. This is basically the topic of this talk, so let's get into it. What? So neutrinos are not to be confounded with neutrons, although they share a similar property that they do not possess electrical charge. So this is great because, like I said, they're going to be able to travel through space in a straight line, which allows us to figure out where the source of our messenger comes from. And so I'm going to show you the international recognized symbol of the neutrino. It's this one. It has a bandit bandana because it's really sneaky. There's a lot we still don't know about neutrinos. One of the reasons that is because they are extremely light. So unlike the electron or the muon and its fat cousins, neutrinos are at least 1,000 times less massive than an electron. And I say at least because we still can't measure their mass. And that's a big question because we know they must have a mass, but it's so small that we are unable right now to measure that parameter. That being said, there are fun facts that you should know about neutrinos. If you want to carry on to the rest of the presentation, I would suggest you particularly remember the third one, but can listen to the others. So the first thing to know is that they come in 3 flavors, basically a flavor is it's a way to say that every one of these electrons has an association, is buddy with the corresponding electron or electron cousin. So for instance, you're going to have the electron neutrino, which is the buddy of the electron. There's the muon neutrino, which is buddy of the muon. And then there's the tau neutrino, which is the buddy of the tau, which is a really, really big electron. And so that being said, we don't know, like I said, their mass. All we know is that 2 of these neutrinos are either more massive or less massive than the third one. So there's this problem that we called the mass ordering or mass hierarchy, if you want to be more precise. And it's basically we only know a relationship between 2 of the masses, and so we still cannot order them in increasing or decreasing order of masses. So it's a really, really weird particle that we're still pretty much interested in the particle itself. We'll see it later. The second fact that's really fun and actually got the Sudbury neutrino reactor the Nobel Prize in Physics in 2015 is the fact that they oscillate. So oscillation means that a neutrino while it's traveling through the vacuum of space without seemingly interacting with anything else in its path. It's going to spontaneously change from an electron to a muon, and then from a muon neutrino to a tau neutrino, or maybe back to an electron neutrino. And so this behavior happens constantly. And depending on the energy or the distance that the neutrino travels, you can end up seeing an electron neutrino as a muon neutrino, or a tau neutrino as an electron neutrino. And so this is a behavior that's really interesting, because it's one of the very few evidence that there is something missing from our what I call the standard model, our understanding of particle physics. So technically, the model that I showed previously does not expect the neutrinos to have any mass at all. And because they have mass, they're able to do this oscillation thing. But it's still the only experimental evidence that we have that there's new physics that we need to search for. And so this is really interesting. But the most mind-bugglingly interesting fact about neutrinos is how they are almost unstoppable, and how they are ridiculously numerous as well. Every second, there are billions of neutrinos reaching us, coming from the sun. And the numbers of neutrinos being emitted by the sun is so ridiculous that you have to come up with some sort of scale for people to realize how big it is. And so after talking to some physicists who all had different idea, I settled for this one. If you look at your thumb, every second there's 10 billion neutrino crossing the surface of your thumb that's coming from the sun. And so this is basically, there are as many neutrinos crossing your thumb right now, every second, as there are water droplets falling off Niagara Falls in 1 second. That's about the scale. And what's even weirder about this is, even though you have tens of billions of neutrinos passing through you every second, or in your entire body is probably going to see only one neutrino interacting in your entire lifespan. So this gives you an idea of how rarely a neutrino interacts with anything, whether it be us or whether it be the entire Earth as matter. And so over billions of septillions of gazillions of neutrinos that reach the Earth, there's probably going to be like one or two that are going to reach us and actually interact inside the entire Earth. And so to catch a neutrino is a big challenge. And so the reason is that you need a lot of matter. You need basically a big target to make sure that there's a reasonable probability that neutrinos are going to interact. And so how can you go about and find this volume? You necessarily have to use a really big experiment, a big volume of matter. So there are many ways you can do it. One way you could do is do like they did at Snow Lab at the Sudbury neutrino reactor, and it's, build a mine, coat it with cement, make a clean room facility, take time to sanitize everything, then install this gigantic ball that holds a ton of water that's been extremely well purified, or introduce in that water organic scintillator that takes years to develop and process and actually produce. Then figure out all these fancy, really hard to design electronic equipment, and then take some measurements. So that's the hard way. The other way you can do is just take some ice, but a really big piece of ice. And I'm talking about something like a cubic kilometer of ice, and just stick light sensors into that block of ice, because it's still a big target and neutrinos are going to interact. And one thing I forgot to mention is that you need a transparent medium. We'll see later why this is the case. But so the experiment I work with chose the easy way, if we can say so, by building a cubic kilometer detector at the South Pole in Antarctica. And so this is IceCube. So like I said, it's an experiment that is located at the South Pole. It consists of 86 strings of light sensors that have been placed underneath the Antarctica ice sheet at a depth of 1.5 to 2 kilometers. And so you can see at the Eiffel Tower as a scale, it's a huge volume of detection. And what the goal of this experiment is to detect those high energy neutrinos that we think are coming from astrophysical sources. And so with this cubic kilometer of ice, it was thought at the conception that we could detect the very high energy neutrinos that would come from that blank spot that we saw on the previous graph. And so how would you go about to build such a detector? Well, one thing you can first have to do is you have to drill holes in the ice. To do this, you cannot use mechanical drills because the hole is way too deep. You have to use hot water drills that are going to heat up water to about 90 degrees Celsius and then inject it at high pressure and basically forge and melt the ice over the entire depth of the ice sheet, which is about 2.5 kilometers. And so once you've done that, you have a hole that has water in it, and the water takes a couple of months actually to freeze out. So you have some time on your hand. And so while you have that time on your hand, you can take these detectors that are called digital optical modules, or DOMs. They're about this big, and they are pretty heavy because they are encased. So the light sensor is the bubble at the bottom, and that bubble and electronics on top is encased in a glass vessel that's about a centimeter thick to withstand the ridiculous pressure of ice at a depth of 2 kilometers. So these pressure vessels and those detectors are arranged in a string, and then that string is then lowered inside the hole, and then the hole is left there to refreeze. And so when you've done that over many seasons and look at your array, what you have is this, which is a transparent medium with a couple of detectors on the way. Now you're ready to look at neutrinos interacting. And so the way an interaction happens, the way you can detect that a neutrino has actually hit your detector, is that whenever a neutrino comes in, for instance, a muon neutrino, and it decides to interact, what it's going to do is it's going to turn into its equivalent buddy lepton. So basically the muon neutrino is going to turn into a muon. And that muon is going to carry on and travel in the same direction as the initial neutrino. However, because that muon is charged, and because it's traveling at really, really fast speeds, it's traveling so fast actually that it's traveling faster than the speed of light in ice. That effect of a charged particle moving faster than light in the transparent medium produces a wave, basically a shock wave of light that we call Cherenkov radiation. And it's going to produce light that's in the blue to violet range. It's going to emit light in the ice. It's going to last a millionth of a second. And then it's going to trigger some of the detectors around, because these detectors are sensitive enough to detect single photons, single light particles. So here's an example of a real event. What you see here is the event that's been... I'm going to start the movie, but just to explain what we're looking at. So these vertical lines corresponds to the string of IceCube. And the little beads around the string every bead corresponds to one light sensor, one DOM. And in that simulation, the size of the DOM is going to correspond to how much light that particular DOM has detected. And the gradient color that you see is basically the time development of the event. So light, red means light that has arrived first, and then green, light that is being detected later. And so we can see what a muon through the detector looks like. Is it working? Well, Oh, okay, there it is. Yeah. Oops. Yeah. So it starts. So it starts inside the detector, which means that the neutrino was inside the detector and then suddenly turned in the middle into a muon, which is a very good way to know that it's actually a neutrino. And then what you see is basically the track of the muon, so you know that it's coming from a bit upwards in direction. So this is a real event that's been detected. So that basically answers the next question. After 6 years of operating IceCube, did we succeed in detecting high energy neutrinos from outer space? Well, yes. So that was a proof. It's not a simulation. And actually, we've detected way more than just one. So far, this is what our map of the universe looks like in high energy neutrinos. It's a collection of a little over 80 individual neutrinos that have come to us from various parts of the sky. So what you see here are not actual sources. And this is a problem because what you see here are just counting individual neutrinos in the sky. And one of our biggest challenge right now is to try to see what sort of sources can produce that. Was there a question? Oh, okay. So yeah, our biggest line of investigation right now is try to figure out what is producing these high energy neutrinos. And while we don't have an answer to that yet, I mean, your guess is as good as mine, although probably not. I know a bit more. So I'm going to just go into one astrophysical phenomenon that we think produces neutrinos. It's highly likely that it's one of the producers of these neutrinos, and that's called a supernova. So most of you probably know about supernovae. They're big explosions in space that occur when a star that has about 40 times the mass of our sun collapses under its own weight. And the way this explosion happens, according to the most recent modeling of the phenomenon, is that our sun is currently burning hydrogen, which is a light material, and fusing it using nuclear fusion into a heavier element, which is helium. Once it's going to be done with that, it's going to take helium and fuse it again to make another heavier element. And so stars in general have this way of producing onion layers, like the one you see on the left, where there's layers of denser and denser material. And in the case of a very massive star, like one that's 40 times the size of the sun, this process ends up building a big core of iron at the center of the star. And that core of iron cannot move further into the change of fusion because it's too difficult to produce something heavier than iron. And it's just going to grow. It's going to grow, and become so heavy that it's going to collapse under its own gravitational weight. And so what this means is that you're going to have a core that's going to shrink to the size of about a neutron star, which is a couple of kilometers, in the span of a fraction of a second. And that's going to produce a big shock that's going to bounce outward. There's going to be a shock wave of energy that's going to be emitted outwards of the star. And that shock wave is believed to be the mechanism by which matter outside of that iron core is ejected in what we call a supernova. The problem with the modelings is that so far it's been difficult to explain how that shock wave is able to propagate through matter. It's able to push basically all the atoms, all the mass of the star outward. And the more reasonable explanation, which is still ludicrous, is that neutrinos are actually the particles responsible for pushing that matter. Now, I don't know about you, but I don't want to push a 40 solar mass star. It's heavy. It's really, really heavy. And can you think of anything that could push that matter outward at huge speed and produce an explosion like this? Especially when you think that neutrinos are really, really, really light. Like I said, they're about 1,000 times at least the mass of the electron. So to me, this process looks like you're trying to bring a car from 0 to 100 kilometers an hour by just throwing spitball at it, like with the straw. You must need a lot of these spitballs. You need a lot of neutrinos. Similarly, really a ludicrous amount of neutrinos to be able to push the mass of the star away and produce that explosion. And so far, it's the most likely candidate that we have of an astrophysical source. Now, so that's the astrophysics that we do with neutrinos as cosmic messenger. But we're also wondering about the neutrino itself. Like I said before, neutrinos are weird particles that we don't fully understand. And so it would be nice, given that we're a neutrino observatory, if we could figure out and measure properties that relate to the neutrinos and its declination. And so what's interesting about IceCube is that the event that I showed you, the 80 astrophysical event, they're really high energy. And so these events don't happen often in our detector. However, neutrinos that are produced by the sun and neutrinos that are produced in the atmosphere are more, they interact more commonly inside the volume of IceCube. So much so that we have a lot of events of neutrinos of lower energy that we can use to try to make particle physics with a telescope, basically. And so this is the research that's my group is mostly interested in at the University of Copenhagen. We look at very low energy, low brightness events, so not these ones you saw, but some that are really smaller, much smaller events. And we try to answer questions like, how do they oscillate? What are the parameters of this oscillation business? We want to see, is there a mass that we can measure, or is there an ordering? Can we help trying to figure out how can we order the neutrinos in terms of mass? And similarly, there's another question that lies around, is whether or not we've found all the types of neutrinos. Because there are a lot of theories out there that suggest that there would be what's called a sterile neutrino, which would be this guy, and which would be another neutrino that somehow does not interact like the other three, and that could be responsible for what we call dark matter. So there's also a component of the science that's being made with IceCube that has to do with dark matter searches. And doing neutrino physics is fun, but it's not as sexy to show on a presentation than showing cool plots of a supernova, for instance. Everybody loves stars and explosions, but it's kind of particle physics is a dry subject. And so rather than try to show you some results, I figured I would show you how doing particle physics can really bring about the artistic side in the physicist. So this is an example. So these are actual results that IceCube has published relating to dark matter searches and neutrino physics. And what I've done is basically remove all the labels, all the scales, and all the numbers, so that you can really appreciate the beautifulness of the curves and the colors, and really reflect on what this picture really means. Because this is actually what we do, even when there's labels, and there's a collaborator, for instance, who's going to come up with a plot like this. We could take hours in our group meetings to even try to understand the meaning of those plots. So it's really similar to what we could say contemporary art in some way. There's a lot of interpretation that has to go on. And so this is probably the weirdest. We can play a game of which one is the dark matter limit and which one is modern art. And so more seriously, these plots, what they show is they are constraining the parameters of whatever matter you're trying to search. So for instance, when you look for dark matter, you have to imagine that dark matter is something. So you come up with an idea of, oh, I think dark matter is going to be a particle that's going to have this mass, or it's going to look like this, and it's going to interact like this. And then these graphs can tell you, because we haven't observed this amount of flux or neutrino, because we haven't observed anything, you can exclude this range of mass from your searches. And so this is how most dark matter searches, by excluding regions of the parameter space, as we like to call it. So this brings me to the conclusion of this portrait about cosmic messenger. So like I said, neutrinos are great because they could open up a new window to astronomy, as well as help us understand the fundamental physics of our universe. But neutrinos are not the only messengers. And just because photons are not perfect messengers, that doesn't mean that we have to throw them away. There's still a lot of phenomenon that we need to explore in gamma rays, for instance, to better understand. And so with the mixture of different messengers, I've labeled different experiments across the world that work with these different kinds of messengers. So you see IceCube on at the bottom on the South Pole. There's SNOLAB in Sudbury, and Antares in the Mediterranean Sea. So what you can see in this legend is that I've also included two other messengers that I haven't talked about. Well, I've talked about cosmic rays and told you they were useless. That was sort of a lie. They're useless. They are very tricky because you cannot pinpoint the source of these charged particles, which we call a cosmic ray. But by just collecting them and measuring their individual energy, you can still try to understand the physical processes that ended up producing such high energy particles. And so in that way, cosmic ray is really useful because because the higher energy the particles you detect, you have to come up with a physical explanation for how these cosmic rays were produced. And so far, this question is far from resolved, and there's a lot of intensive research going on with respect to cosmic ray. And then the other messenger I haven't talked about is not a particle, so it does not fit in the standard model of particle physics. It's gravitational waves. If some of you have been at some previous AstroNights, you've probably heard about gravitational waves. They're basically ripples in space-time that are produced when massive objects collide with each other, like two black holes. These ripples propagate at the speed of light through space-time and then reach us. And if you have a $1 billion laser interferometer, like LIGO does, you can detect this a tiny distortion in the space-time around those detectors, and hence you can detect black holes merging, apparently. And so what this shows you is what a lot of high-energy astrophysicists, high-energy particle physicists are calling multi-messenger astronomy, or multi-messenger high-energy physics. And so this is believed to be the way of better understanding our universe, better understanding the violence behind some of the processes in the universe through the use of many different messengers, and hence get a more complete portrait. And so that's the end of my formal talk. The next couple of slides are just cool pictures of the South Pole. No pun intended. So this is the IceCube Laboratory. So this is the station where all the cables from the cubic kilometer detector ends up. It all goes into servers in that room. The servers and machinery in there processes the data and sends it via satellite to the north, to our collaborators. We're a worldwide collaboration. There's something like 42 institutions in many countries, Europe, Japan, the US, and Canada as well. And so this is where people have to maintain this equipment if we want to gather quality data, because if a server fails there, someone has to repair it. And to do that, there are many trips that you can do during the Antarctic summer. So there are usually 5 people in the collaboration that have the chance of doing actual work at the South Pole during the summer. So they enjoy the sun, they enjoy the warm minus 60 degrees Celsius, and they do their business for a couple of weeks and then they come back. And then on the other side, to take care of the experiment year long, you need to have what are called winter rovers, and those are 2 brave individuals who will tend to the detector for the entire Antarctic winter, which means they're going to work 6 months into total darkness. And they're going to basically end up spending a year at the South Pole, first arriving in the summer, getting their training done by the former crew, and then watching everybody leaves on airplanes and gather. There's about 40 people staying the entire winter in Antarctica. And the reason why they have to stay there is because it's so cold that hydraulics in planes can freeze. And so it's extremely dangerous to fly at the South Pole during the winter. Also, the visibility is terrible. So they are isolated from the world over a period of about 9 months. And so to do that, they have what's called a South Pole Station. So this is a multi-science station that was already there at the South Pole. There's a lot of other experiments going on there, astrophysics and others not related to astrophysics, really. So it's got facilities for people to live in. It's got greenhouses that are able to, if I recall, because I've listened to a talk from previous winter rovers, and I think they said they could get like a fresh salad every week from that greenhouse in the summer, which is always appreciated. There's a gym which serves over the winter solstice, so during the longest day of the Antarctic winter. Everybody gathers in the gym and watches all 3 versions of The Thing, which is apparently a movie about the South Pole. And so they dim the lights, and really, really good for the morale. It's a tradition, apparently. And well, in the summer, it's summer, so let's do barbecues at minus 60. I think that's actually one of my colleagues who went to the South Pole, Morten. He's Danish, so he has to show that he doesn't care about the cold. And so this is, that's also the ceremonial South Pole. So the actual true South Pole is moving away from our detector, or actually the entire station is moving away because the ice on which it resides is slowly drifting. So there's actually some science in IceCube that has to do with glaciology, and recently there's been talk about asking glaciologists what was going on, because we need to understand ice. Yeah, sorry, glass. Yeah. Ice as a medium. So this is what happens. So the next few slides are just rip-offs of Game of Thrones. Winter is coming. The sunset, it's nice. You can take beautiful pictures of the sunset because it lasts for 2 weeks. So like the winter over told us, you can take all the time you want to get the perfect picture. Just wait for the sun to line up. And then once winter has come, it's the long night. So there aren't White Walkers so far, but it's really dark. And like I said, there's no planes that can land unless there's a medical emergency, which happened last winter. So they had to fly in a plane. And so the picture you see on the left is actually probably 1,000 times brighter than what it's actually like when you were looking at this, because it's a long exposure shot. And so they had to fly in a plane, and because they can install electrical lighting to show the landing strip, what they have to do is basically put enormous barrels of fuels on fire and just light them up all across the snow landing strip so that the plane can hopefully arrive safely. But all is not dark at the South Pole. Usually the winter rovers, which are, like I said, about 40 people, they form a really closely knit community that support each other and always find reasons to celebrate or have a party or lift the mood of living, which is hard because you live and you work 10 hours in the dark and then you sleep in the dark for 6 months. So this is, for instance, they have celebration on Christmas in July, the 25th of July. And at the bottom last year, the two winter rovers from IceCube, they decided to make an igloo. A project that, according to them, initially should have taken 2 days. It ended up it took them like 2 weeks. Turns out building an igloo is quite complicated, structurally speaking. Another one is they watch, I think, the Euro live. They managed to get a live connection, which is rare. Like you don't have the streaming speed to watch Netflix. So the communications out to the outside worlds are usually limited to emails without pictures because usually when everybody's online at the same time, they all send their emails right before lunch at 5 and the system goes down and you can't really send stuff. But they were lucky enough to show the final, I think, with Germany. Right up until 10 minutes before the end of the game, they lost connection to the satellite. And so one of the person in that picture called his or her mom via satellite phone. And so the mom just placed the phone right next to the television. And so they could hear they managed to hear the last 10 minutes of the game. That's pretty cool. Finally, I mean, there must be some upsides to living in the dark. You can watch beautiful auroras all the time. This is basically the night sky. You can take amazing astronomy pictures like they did. Beautiful sightings. Yeah. And so... yeah, we are really grateful. We're really grateful for winter rovers because they're the ones ensuring that 99% of the time our detector is running fine and collecting data. And so we have vested interest in the sanity of winter rovers. So we want them to have a good time and not cut wires where they shouldn't. So yeah, that's about it. So if you have any questions, thank you. Yeah. Yeah. This guy, this map, yeah. Yeah, you mean given the distribution of the neutrinos, are we able to see, well, there seems to be more neutrinos in the center of the galaxy, for instance. There's been a lot of searches to try with likelihoods and probability models that try to fit the spatial distribution that you see here. And so far, there's no correlation between the location of these neutrinos and the center, for instance. It's basically a map that's gonna look a lot like the cosmic microwave background. So it's you look at the space and you ask yourself, what is the probability that that neutrino comes from the same place as this one? Yeah. And so far, there's you can see structure that look a lot like yeah. It's really at the beginning. This guy, right? You could see structures like that, and this gives you a map of the probability of there having a concentration of particles that come from there. However, you have to be careful when you look at those probabilities, because the more you search for something, the more likely you're going to be able to see it, especially if you try a million different hypotheses. There's a significant chance that you're going to find something if you start looking a million times at the data. And so that's something that's really difficult in low statistics physics, like particle physics, because it's called the look elsewhere effect. It's basically if you mix your data a lot, like a gazillion time, you cut it and you arrange it, try different scenarios. The more scenarios you try, the more likely you're going to be to find one of these scenarios to match by pure coincidence. And so far it doesn't show any sources. Yeah. Yeah. Yes. Yeah. Yes, although the neutrino, so the neutrino is able to turn into a muon because it's traveling extremely fast. So it has a lot of kinetic energy. So it's the kinetic energy, the energy of motion of the neutrino that converts itself into a new particle that produces. I don't know. Yeah. Oh, I mean, I'm more of an experimentalist. I look at data and I gladly say to this theorist, "You're wrong. You're wrong. You're wrong." But that's what we do in experimental. I don't know. There's a good chance that supernova are involved in neutrinos, because actually the first extragalactic neutrino that's been detected was back in 1987. So there's been a supernova that exploded, and people were able to detect a neutrino that arrived much at the same time as the explosion. So you can't say it comes from a supernova because you couldn't locate it in space, but it was a neutrino that arrived like visibly after a supernova. So it's a pretty reasonable assumption that supernovas cause at least some of the neutrinos, but yeah, so I don't know. Yes.
There was this experiment with a big round thing.
Yes.
Purified water and super clear, and you said it was really important that it was clear, but then you say they drill holes in like ice that has been naturally made. Is it like super clear ice?
So, yeah, that's a very good question. The answer is no, and the second part to that answer, it's causing a lot of problems because ice is not homogeneous. Ice has piled up in Antarctica over eons, geological eons, and so it has different optical properties, and there's different amounts of dust. So, for instance, we know that about midway in the depth of the IceCube detector, there's there's a layer of dust, and so there are particles inside the ice that scatter the light a bit more, and that produces a lot of problems when you try to analyze data that comes from this region. And so this is why there's a lot of effort in calibration to try to understand the ice, but it's a difficult medium. Yeah, I think. Yes.
What motivates the belief that might exist? Is there some unexplained experimental data, some theoretical prediction?
It's probably a mix of our knowledge of. First, if you have sterile neutrinos, it changes the evolution of the universe. So at the if you think of a new particle, you need to think of reasons how it would affect the universe, because the hypothesis is that that particle existed at the Big Bang. So if you have neutrinos in your scenarios with the universe, how maybe that could explain some of the answers they have. I'm not a cosmologist, but that would be an area. Like I said, dark matter is another sort of blind search where we try to come up with any sort of explanation as to what this matter is made of. And so as long as it fits the observations that we're seeing, it's a difficult way to disprove theories completely, because you always have a range. Like you can say, oh no, my neutrino is not, it's because it's only interacting with this guy, and it's because it has a very particular mass or something. It's
Unfortunately, probably time for like one more question, and then we'll
Yeah.
wrap things up.
sure. Yeah, I think you.
Alright, so you know when a neutrino, like a muon neutrino, turns into a muon, and the muon like interacts with the other the detectors. I know that because you have conservation laws that you have to respect, for example, the conservation of charge and conservation of
You don't have to conserve charge in those interactions. Well, yeah, actually you do, but you do it through, because neutrinos interact through the weak, what's called the weak nuclear force. And so you have to invoke one of these Jedis from before, because that Jedi has the charge, and it leaves with the charge.
Yeah, but then the W boson that has a charge, I think it will decay into, like, if I'm not mistaken, an electron or something, no, a positron and anti-electron neutrino or something like that. But do these particles interact with the detector? Because I know the muon.
Usually, I don't think so, because if that particle decays back into a neutrino, that neutrino is gone. It's not. There's no chance that there's going to be a second interactions. But we know that there are some instances where maybe you can distinguish between types of neutrinos by looking at the products. But it's really difficult with the resolution of the detector to see anything other than a line or a muon. So, yeah, that's about it.
Let's just thank our one more time.
Thank you.